Good evening, everyone. My name is Daniel Zakri bin Hajar Maidin. My matrix card number is 01DAD23F2007. And today I'll be presenting about our case study for vehicle dynamics. So, this is the introduction. Aerodynamics is important in vehicle design because it affects fuel efficiency, speed, and overall performance. One of the main forces acting on a moving vehicle is drag force, which resists the vehicle's motion through air. Drag force depends on factors such as velocity, air density, frontal area, and vehicle shape. The drag coefficient CD shows how aerodynamic a vehicle is, where a lower value means better efficiency. In this study, the drag coefficients of 3 different vehicle models are calculated and compared to understand how vehicle shape affects aerodynamic performance. Okay, our objectives for this case study is to calculate the drag coefficient for different vehicle models. The second one is analyze relationship between velocity and drag force. And the third is understand effect of vehicles shape on drag. So these are the specifications and example of cars for the dimensions of each vehicle. So we have 3 models, model A, B and C. Model A is a compact car with a streamlined design, expected to have a low drag, and in the picture that is a Mercedes CLA 45. So for the model B is a Toyota Camry. This is a mid-sized vehicle with moderate aerodynamic features. And for model C, which is a Rolls-Royce Cullinan, a larger vehicle with a boxier shape, likely to experience higher drag.
Assalamualaikum, my name is Muhammad Ahmad bin Azwan. My number matric is 01DAD23F2004. So I want to tell about calculation of vehicle model A. Based on the table, firstly, velocity, the value is 100 until 200. Secondly, drag force, the value is based on velocity. Thirdly, frontal area, the value is same from 100 until 200. Fourthly, air density, the value is same like frontal area from 100 until 200. Fifth, drag coefficient, the value is same like air density, frontal area based on velocity. So the calculation of model A is length is 3.8 meter, width 1.5 meter. For the frontal area is 75% times 3.8 meter length times 1.5 meter width, and the answer is 4.275 meter.
So right here we have the calculations for model B. So starting we have velocity, which will increase from 100 milliseconds all the way to 200 milliseconds. And then we have drag force, which will slightly increase as well based on the velocity. And then we have force area, which is the same for all, which is 5.1 meters square. And then we also have air density, which is also the same, 1.225 kg per meter square. And then we also have the drag coefficient for it, which is 0.1342. And the model B, which length is 4.0 meters, and then the width is 1.7 meters. So the frontal area of it, we have to take the 75% times 4.0 meter, the length, and times 1.7 meter, the width. Hence we will get the force area of the model, which is 5.1 meters. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Atika binti Fairul. My matric number is 10DAD2F2005. This slide presents the drag force analysis for model C. The model has a length of 4.3 meters and a width of 2.0 meters. From this, the frontal area is calculated as 0.45 square meters. The table shows the relationship between velocity and drag force. As velocity increases from 100 to 200 meters per second, the drag force also increased significantly. For example, the drag force rose from about 249 Newton to nearly 99 Newtons. This clearly shows that higher speed results in higher air resistance. In conclusion, drag force is strongly affected by velocity in Model C. This slide shows the graph of drag coefficient versus velocity. From the graph, we can see that the drag coefficient remains constant for all velocity values. Each line represents different models, and although the values are slightly different, they do not change as velocity increases. This indicated that the drag coefficient is independent of velocity in this analysis. In conclusion, while velocity affects drag force, it does not significantly affect the drag coefficient for this model. This graph shows the relationship between velocity and drag force. Unlike the previous graph, we can clearly see that the drag force increases as velocity increases. The drag is not linear, but gradually becomes stable, showing a significantly rise at higher speeds. For example, the drag force starts at around 250 Newton and increase up to nearly 1000 Newton. This indicates the drag force is highly dependent on velocity, where higher speed result in much greater air resistance. In conclusion, increased velocity has a strong impact on drag force. Next, we will discuss the result obtained from the analysis based on the data collected. It can be observed that Model A has the lowest drag coefficient among the two models. This indicates that Model A has the best aerodynamic performance because lower drag means less air resistance acting on the vehicle. In contrast, Model C records the highest drag coefficient. This is mainly due to its large frontal area and less streamlined body design, which increase the air resistance when the vehicle through the air. Meanwhile, Model B shows a moderate drag coefficient, meaning its aerodynamic performance is average compared to Model A and Model C. Moreover, based on the comparison, Model L demonstrates the best overall aerodynamics efficiency, followed by Model B, while Model C is the least efficient due to the highest drag value.
Effect of velocity. Drag force increases rapidly with velocity because it is proportional to the square of velocity. This means that small increase in speed can lead to large increases in drag. Firstly, source of error. Assumed air density may not be accurate. Simplified vehicle shape measurement inaccuracies. Secondly, improvement. Use wind tunnel testing, more accurate measurement tools, consider real-world conditions. In conclusion, this study successfully analyzed the drag coefficient of 3 vehicle models. It was found that aerodynamic design plays a critical role in determining vehicle efficiency. Model A demonstrates the best performance due to its streamlined shape, while Model C experienced the highest drag. The result confirmed that reducing drag can significantly improve vehicle performance and energy efficiency.